It works.
Everybody hear me? Great. Thanks all everybody for coming out today. It's our developers conference. Again, for those of you who were here yesterday, thank you again for coming. Great seeing some people last night at our reception. I had a lot of fun. I hope everybody else did. I guess sorry for the rain. I was told it rained. I was like there the entire night, and I came out and it was like humid, but that was DC, right? But I guess it rained a lot. Okay, so this is the first day of the developers conference. We've got 3 days of talks planned, followed by our Friday Hackfest. We'll explain a little bit more about that for those of you who are a bit new to the kind of community and concept of this. But just to give us a quick start off, I really do again want to thank our sponsors. A lot of them have booths out there that you can go and check out, see their wares, see their ideas. But they really help hold us together and make sure that this works. And things like the reception and the banquet tonight are all possible because of the support of a really great group of sponsors and companies who really pull everything together for us. The other people that pull everything together for us are our organizers and the volunteers. So I want to give them a shout out to make sure that they're recognized for the work that they've done to help us make sure this gets put together on time and tells me when I'm wrong and tells me what to do when I have no idea what's going on with the next part of the conference. So we'll say more about them later as well. All right, this is the conference overview. If you go to, on the brochure that was handed out, you'll see this image, the handout, basically the program for the event. Mostly just look at the front page and it links to the website of the conference, right? www.tronda.com/grcon15. The agenda is posted there. There is also a short list as far as like the title and the times of all the talks for the rest of the week. So you can go there, check that out, see what's being discussed and talked about at different times. Then there's a presentation. If you go to, there's like a menu for the conference. There's a presentations page as well as the kind of short agenda. And in the presentations page is the abstracts. Not all abstracts are there right now. It's just kind of the title and time and speaker. But eventually we will have all the abstracts up there as well as the presentations themselves. So we're trying to make all the presentations that we can available to the community after this is over. And we're recording, so with luck, we'll have good audio and good video quality, so we can edit this and post these online in a few weeks to months, depending on how gung-ho we are about getting that done. So we haven't recorded the GRCon for a couple of years now. It's something that people ask about. I think it's a good thing to get out there because there are some really good talks. A lot of good information comes from everything in this conference. So this year, hopefully, we'll be able to post these online and make sure we have a record of all the cool stuff that's happening and being talked about. Let me talk. Actually, let me just make sure I know where I am here. So this is the agenda. You can see here. Maybe I'll flip back and forth between these two pages. Starting Tuesday, Wednesday, Thursday. Kind of switching up our opening a little bit. Hopefully we won't talk for 45 minutes. We want to give our keynote a little bit more time. And I'll introduce the keynote, Joe Mitola, in a second. But we have a few things to kind of point out about kind of the nature of the agenda. First off, we have, aside from myself and Jonathan Corrigan, who not only help run the project together, we sponsor the program, we are responsible to the conference as well, but our kind of 3 other big platinum sponsors who really help us with support, both financial and people that work with us on this. So they're kind of given a day each. It's kind of like a sponsored day. So each day we have a different kind of sponsored talk. Right, so they help us with the projects. They get some time to address everybody. So we'll do that. Mostly they're going to open the day like tomorrow and Thursday. We've got our keynote first, and then we'll hear from Matt Edis after a break. Most everything else is separated. Let me just go to this concept here. Separate kind of color coded as far as what's happening. So you'll see apps and research and tutorials. So I just want to explain a little bit about what that means. I guess the only distinct difference back here is one of our apps and research is what we famously call the Baldwin Show. For those who have not seen the Baldwin Show before, by the time he's done, you'll know why we give it its own special name. But we have, we separated the tutorials, and I know that's kind of a weird naming, because tutorials tends to mean these like hands-on tutorials, like what Jonathan did yesterday, where he walked through, going through like building an FM receiver. In this case, these are lectures from more core developers in the project, talking about new things that we've developed, or specific applications, or specific pieces of GNU Radio, to try to give everybody a little bit better feel for all of the things that are within this GNU Radio package. So they're kind of more tutorial-ish talks about the project. Apps and research are more related to what the community has submitted to present at the conference. So these are users more than, they're developers in their own right, but they're more users of GNU Radio to develop their own work in applications and various research programs. So that's where you'll get a lot of more information about how GNU Radio is being used in the community. Talk about the sponsor talks. Let's see, so we got RFNOC and the working groups. So I just point those out. The working groups are a part of the project that helps us focus ideas, try to solve the big problems. So these are, we have 6 of them. We have a working group leader for each of these. So they're really trying to solve some of the bigger problems that we see in the GNU Radio community. That number may grow, perhaps eventually it may shrink once we solve some of those issues. But they're focused working groups of developers. We're having sidebar working group meetings at the end of each day. So it's a parallel track to the main conference track. So we'll still have talks going on here, which is where I envision most people will want to be seeing the talks. The working groups will be in the concourse level. So there is a printout. We put up on the web page, and what's on the pamphlet? Does the pamphlet have all 3 or 2? It has the 2 floors, I believe. So we're on the 2nd floor. If you're looking at the layout of the CSIS building, we're on the 2nd floor technically. Below us is the 1st floor and ground floor, and then below that is the concourse level. So these sidebars that we're going to have, these working group sessions, are on that concourse level in what we're calling the IEQ rooms. So each day, so I pointed out there, so like today we have the embedded systems working group in the I room and the community working group in the Q room. So if you are interested in one of those working groups on any given day, look at the program and figure out where those working groups are being hosted, which room they're going to be in, and find them during that time period. Like I said, they're generally focused. They're generally there's a set of developers, but we are open and welcome to new people who have an interest in a particular area, because we do want to grow these working groups as far as the people that we can go and talk to and work with and feed us good information and hopefully actual development work on these big problems. If you want to learn more about the working groups, as I said, there's 6 of them. There are posters, so as soon as you come on there, you've probably already seen them because you come up the stairs. As soon as you walk out of this room, we have posters up there describing the work and the purpose of each of the working groups. So if you want to know more, figure if maybe I am interested in helping the community grow. So let's see what the community working group is doing. The coprocessor, right? We want to figure out how we can use coprocessors and hardware accelerators integrated into a GNU Radio structure to speed up and specifically hardware support. So that's like a focus of one of them. The GNU Radio Companion is, it's a big part of the project. Everybody loves to use the GNU Radio Companion, but everybody uses it. You know that there is a lot of work to be done there. It's a full feature system, but there are so many other features that we want to do. There's so many other advancements to that project that we want to see. So we have a working group dedicated to that. The final day, you'll hear about Volk, our Cindy optimization library. So we'll talk about that on the last day. Nathan will give a talk, I believe, tomorrow. So we'll talk more about the details of Volk, but there's a working group on that. And there are functional architectures, trying to understand how to grow the fundamental project of GNU Radio to support more evolved modems. So that's probably our newest working group, and still kind of developing its concept there. Details on the posters, and you're welcome to come and join us if you are interested in any particular problem area. The kind of second breakout session, again, it's going to be in the separate room, the Q room on Wednesday, is the RF knock. So tomorrow morning, during our tutorial section, we're going to hear about Vulkan, we're going to hear about RF knock. So you'll get a basic overview about what RF knock is and what its purpose is for, and kind of how to look at it and how to use it. Edis Research is hosting a tutorial, but as we try to make sure everybody who signed up for the conference is aware, that is you have to pre-register for that tutorial. So if you're not pre-registered for that, I'm afraid you can't get in, but just hardware limitations, because it is a very popular, very kind of new, cool concept. So we're hosting that, and I'm sure you'll see a lot more available information and tutorials and training for RF in the future. Finally, on Friday, so the developer conference really is the next 3 days, and we'll technically close it out on Thursday afternoon. But Friday we have this all-day Hackfest, and if you're not familiar with the Hackfest, you might have called them code sprints. It's another term that we use, maybe a bit more professional term that you might want to sell it to your bosses with. These are, in the GNU Radio world, we get together the main core developers, and we're trying to, we kind of grow that core development team, as we go along. Get together often for week-long stints of Hackfests. Edis Research often hosts them. We did one in the Netherlands earlier this year before our FOSDEM conference. We did one in Karlsruhe. So we do them all over the world. Well, all over the world. So far Europe and America. But we do like to do these in different areas to attract different groups of people to the project and to the development community. They're great ways to get together, sleep way too little, have way too much caffeine, and work too hard for 1 week to get a lot done. It's a great model that's completely unsustainable for probably more than a week. But we do get a lot done in those weeks. This is kind of a little mini Hackfest on Friday. We like to do this after the conference. A lot of ideas flowing through the community, through the people that come to these conferences. A lot of questions, a lot of ideas. This is kind of a way, it's a little bit more of a free-for-all, but it's a little bit of a way for people to talk to us, to work on a project, to find your own community of people interested in the same things that you're interested in, to see if you can start getting some projects started and working. They are free for all. You are welcome to do whatever you want at Hackfest. It's going to be in this room, but just figure it out. We won't have presentations, like formal presentations. So you just come in here, set up, bring your radios, bring your laptop. We'll have our stuff and just go and work. But if you're not comfortable with that, or you don't have your idea, maybe you're too new to the project to really understand, what your thing is that you want to work on a day like this, there is on the conference website, there's a Hackfest page where we have given, I think there's like 12, maybe 13 topics of interest that we as a community, as the developer community, kind of decided that, hey, these are things that we think are important, and we think that they're good entry points and things that we can work on in a day. So you can take a look at that and see, oh, hey, maybe I can contribute to this thing. Maybe I'm interested in code optimization, so there's a few code optimization things. Documentation, we talk about this all the time, how much we would love to improve our documentation. So that, which is not necessarily a coding thing, right? It's helping us out with that. So take a look at that webpage if you're interested and see what kind of ideas that you might be interested in. And we've identified kind of an organizer for each topic. So just go and talk to that organizer and get a feel for what that is about a little bit more. Mostly, like, the organizers aren't supposed to be like the leaders. They're not going to sit down and code with you necessarily. Mostly it's so we don't have duplication of effort. Right? There's we do a static analysis tool called Coverity to do a check of the code, and that there's a number of issues from that tool that we'd like to address. Some of them are very easy. Some of them are actually kind of one-line fixes often. But if you're going to do that, it'd be nice to coordinate with the organizer, whoever the organizer is on that page. I think it's Doug. He was trying to hide, but it's Doug. But just so that you know that we don't find people attacking the same point, basically. So that's what the Hackfest is. So it's been fun, very informative, and a good way to get introduced to the project from a kind of a coding perspective. Before let me go back to the main agenda, because I'm going to turn this over to Jonathan in a second. Are there any quick questions about the day? Okay, so Jonathan has a few words to say before we introduce our speaker.
Thanks, Tom. And I will make one correction to Tom's comment that the Hackfest caffeine is probably not the most ingested substance. So I just wanted to start the morning with a few comments. I want to first thank everyone for showing up here. I know you're all busy. You all have your professional lives and sometimes even a personal life in this community. And you've taken the time to come hear what we have to say about community radio. We started here, I'm not going to give you a whole history, but back in 2001, Eric Fossum began the Community Radio Project, and it was really a group of enthusiasts that were interested in taking a technology that was primarily used with 6- and 7-figure hardware devices and either high-end FPGA type environments or dedicated DSP environments. And their objective was to bring this technology sort of to the masses. So we had the radio a couple years later. Matt Edis got involved with the development of the original use of one hardware, and we see how well that's turned out for everyone with the proliferation of not only the Edis research products, but all of the other companies that have come into the space now following Edis research and producing the class of devices that they do. And so that brought in a lot more users to the community radio community, and we morphed from kind of an enthusiast hacker, this is fun and cool type environment, to more serious academic research. We still have the core of hobbyists, but we started to see community radio used in wider contexts. And this growth continued as we brought on, again, more academic research. People started to use community radio in environments that traditionally had been held by larger entities. And around 2008 or 2009, we started realizing that there was a community around the software that we needed to organize into a more cohesive mass. And then sometimes it's hard for people to think about how would you form a community around software? It's software. Who does that? But in the open source world, what we get a lot of today still is that people who write code will contribute it back to the project, and then everybody else in the project gets the benefit of that. And so we have this interchange of software and ideas on the mailing list. We have these Hackfests and community events where developers get together. And what has happened now is that we've got these thousands of hobbyists, researchers, academics, vendors, professional services providers that are all interacting and throwing things back over into community radio. So it's kind of like this stone soup pool of ideas and software that's run into what we have now. Now, yesterday we had the introductory day. I think half the conference registered for the intro day, so there's a large number of people here that are dealing with community radio for the first time. And so a lot of you haven't had the benefit of seeing how this has grown from a small community of enthusiasts to what we have. And hopefully over the next few days you can see a lot of the result of that as we see these presentations that we're going to have in the main development track. Well, we did this yesterday, but I'll do it again. How many people here are primarily EE focused? Okay, and CS? Yeah, so we'll continue to make the CS jokes. Now, 2010 was our first community radio conference in Philadelphia. I don't know that we have, 2011 was our first one. That was in Philadelphia. It was about 50 people crammed into a room like those 5 tables. And it's grown since then. We're about 5 times the size 4 years later. So somebody can do the 4th root of 5 and figure out sort of what the exponent is of that growth. I don't know when we're going to hit the S part of the curve, but right now it's been a fantastic ride. I'd like to thank, Tom mentioned the sponsors and the conference organizers. But in particular, there's a few individuals that have made what we're going to have in the next few days possible. Michael Dickens, you can stand. Of course, Tom, Ben Hilber with Edis Research. Ben, are you around? Yeah, let's get it together. Anyway, I just wanted to sort of give them some thank you. Oh, Martin Ron. There he is. Another Edis. Also, we have a long list of volunteers that have worked to help set up the booths, distribute all the material, all of the arrangements for the power and everything have been done by this group. I won't go over them by name, but if you are a volunteer with the conference, stand up. One more round of applause for This facility is quite nice. It's a nice step up from what we've been doing for the last few years. Thanks, Tom. If there's anything that you need from a facility perspective, you can come talk to us. Or we have two, there's Tara and Alyssa. They're probably out actually doing their jobs. But if you need anything at all whatsoever related to the facility, talk to us or talk to one of them. Thanks again.
All right, the most important thing are our banquet nights. So we had our reception last night, but that was a quick, smaller drinks, chatting, hanging out for Monday night. But we do like to have a kind of welcome and thank you for coming and participating and being part of this the conference banquet. So this is full dinner, dinner and drinks. We'll have so it starts at 6 p.m. I think so cocktail reception starts at 6 p.m. 6:45 I think is when they're going to lay out the food. So it's fairly nearby. It's the Mayflower Hotel in the Grand Ballroom. I think yesterday I might have told people just kind of go down to take a left on 17th Street. Don't do that. Take a left on 16th Street. There is a way to get in, but you need car key access on 17th Street, so it's easier to just come in from the front door on 16th, or actually not 16th, but I think it is technically Connecticut Avenue at that point. Anyways, it's Mayflower Hotel, very close by. It's like a 5-minute walk from here. So come if you registered yet or you showed up yesterday. We didn't get the drink tickets into your name badge holder, but hopefully people have caught up with you and given you a drink ticket as you walked in today. If you haven't gotten a drink ticket, please try to find one of the volunteers. Somehow, stupidly, I let Philip Ballister be in charge of the drink tickets. So they're probably all hidden somewhere on this person. But please, that's a drink on us. And then dinner. This place, I've talked to the chef. I haven't actually been there myself, but it should be a fantastic meal tonight. So you're all welcome to come and enjoy that. Okay, but now I would like to introduce our speaker. This is Joe Mitola. There's a lot to say about Joe. Joe and I have known each other. I don't even remember if Joe remembers the first time we met. It was at this cattle farm thing at the SDR Forum in Fort Worth, Texas, where I was just a little grad student who Joe decided to actually have a serious conversation with. And one of the things that Joe always does is challenge you with new ideas. And I think he's going to challenge a lot of us with new ideas today, and that's why we brought him here, because there's a lot going on. If anybody was here yesterday and you saw the talks in the morning with DARPA and SF, you saw that there's a huge push, a huge amount of energy and effort and things to think about in this space. And I think you're going to hear some really interesting stuff coming from Joe Mitola, who, do we actually have it there? Yes, the godfather of SDR, invented the term software radio, invented cognitive radio, really kind of transformative idea person in this space. So please welcome our keynote, Joe Mitola.
was the opening speaker at the first International Conference on Software Radio in 1996, and João da Silva, also an Italian, introduced me as the Godfather, so I'm wearing my Godfather glasses. However, I really need to dedicate this talk to Chip McGuire, because Chip was my advisor at KPH, and I made the mistake of complaining about software radios becoming so complicated that nobody was ever going to be able to figure out how to use them, and especially not soldiers. So in '96, at this particular MILCOM, reality hadn't set in on the path to radio people. So the GRC radio was supposed to have, and I kid you not, 42 different air interfaces. And so I kind of quipped that there would be, the signal school would be full of people spending their whole career in the signal school and they'd never figure out how to operate these tactical radios. So we needed to put some artificial intelligence inside to kind of run the radio as a soldier. And after that conference, Chip McGuire came up to me, the guy with a beard, and gave me his card and said, well, that's exactly what we're doing in my lab, and why don't you stop by sometime? So I said, okay, Chip. I looked at his card and he's in Stockholm. I'm like, sure, I get to Stockholm all the time. I've never been to Sweden. And, but sure enough, a couple of months later, my software radio course was offered in London, Paris, and Stockholm. So I saw Chip, and when he invited me to do a postdoc, I said I'd love to, but I don't have a PhD. So he said, and I quote, "We can fix that." But Chip was the guy that really invented cognitive radio, because when we were talking about how do you take AI and radio and get them together to do something really cool and important, I said, well, hey, we tried all these different terms like adaptive radio and so forth. And they said, well, how about cognitive radio? And Chip said, well, what does that mean, really? And I said, well, the difference between an ant and the anthill is the ant knows that it's an ant, and it goes out foraging and knows where the queen is and so forth, and knows what its job is. And there are 10% of the ants are crazy ants who don't follow the pheromone trail, and so they get off and they find new food supplies. So that would be, a cognitive radio would be a lot like that, but in the spectrum. And he said, huh, so what's the use case? And I said, okay, well, at the time I was still with the SDR forum, and the use case du jour was that a cell site should be able to do an upload. So Orange of the UK, remember this is GSM, was hot. First revenue in '93. By 2003, GSM had contributed $1.2 trillion to Ericsson, Nokia, and Alcatel. So Alcatel wound up buying Lucent, not the other way around. So I said, well, the use case from Orange was to take a vocoder that was friendly to tonal languages like Chinese and so forth, and to upload this to the system. And he said, well, how would that work? I said, well, the upload would come in, and the cognitive radio would examine this upload, determine whether it was safe or not, and then run it in a sandbox to see if it worked the way it was supposed to, and then adopt it. So Chip said, can't, Joe. I said, why not? And he said, and once again I quote, if I have to tell you why not, then you don't deserve the PhD. Uh-oh. This is my advisor talking. So half of you guys are computer scientists, or maybe a third. I'd like to ask a computer scientist to tell me why that particular little use case was impossible. Not just hard, but actually impossible. Do I have any computer scientists who study theory of computing? Okay.
Could you restate the question again?
Right, that's part of the answer, actually. Examine my upload, determine whether it's safe or not, and then run it in a sandbox, and if it behaves the way it's supposed to, then incorporate it as part of myself. So this requires self-referential consistency, and computer science
The halting problem.
It's the halting problem, exactly.
Right.
So I said, Chip, you're talking about curing and girdle and all that halting problem crap? And he said, yes. So I'm like, oh, darn. Rats. So I went back home. A couple of weeks later, I had studied through English translations of Gödel's paper and realized that a radio isn't a general purpose computer. Squiggles in, squiggles out. So at the time, GSM was mostly voice. So voice comes in, it gets digitized, and in a very short time period, with a small collection of state machines, it dumps RF out there, squiggles out, or ingests RF in and gets speech. And therefore, the hooks that Gödel based the completeness theorem on, general recursion, is not required for radio. So I wrote this up to Chip, and he said, well, that's gotta, if you can get that published in the peer-reviewed literature, I'll give you a check mark and we'll call it cognitive radio. So in May of 1999, I published Software Radio Architecture, a Mathematical Perspective. How many of you have read that paper? Nobody. Well, some have, but almost nobody, because nobody reads that paper. It's a bunch of math. Radio engineers aren't interested in that. Thank God Simon Hayden came along and said, you know what, brain-empowered radio, and here's Joe's OODA loop, and here's how it would really work for radio. So the talk today is about Hackproof cognitive radio. So Tom said, when we were talking about what I should talk about, what would be something that would really energize and open lots of new apps for the new radio and make it, elevate it up to the next level. So I said, well, how about Hackproof in a radio? He said, ooh, I don't know. we got a lot of cyber people and IT people feel like, the hardwire networks are kind of battened down pretty well, but God, this wireless stuff is just open for a pass. And so maybe we better, if you give that talk, you'll have a lot of agnostic people in the room, so you'll have to help them out. So the abstract, which is online, is here, and it basically says that we're going to, that this is important. Cybersecurity today is based mostly on discovering zero-day attacks and creating templates and other, deep packet inspection and so forth. And I call that putting a bunch of bottle rockets. Every time you have a new virus template, it's like a bottle rocket. And if you try strapping all these bottle rockets together and letting them off all at once to get you to the moon, what's going to happen? You're going to get a pretty explosion, but you're not getting to the moon. You have to understand F equals MA. So cognitive radio is, Hackproof cognitive radio is about F equals MA. It's like putting a man on the moon and returning him back to the Earth safely. To do that, you really have to do the math. If you don't know F equals MA and how to apply it in the real world, then you're never going to get there. So that's what we're going to do this morning. Do the math, recognize the solution. The GNU Radio Companion is a large part of the solution. And yesterday I had a sidebar with Matt, and where is Matt this morning? Matt, where are you? Is he not here? I'm trying to congratulate him for being the real architect of software radio. The difference between an architecture and a design is a design is a point solution and people throw it away afterwards. But an architecture is a design and a framework that stands the test of time that allows hardware to move out under it and apps to be built on top. And GNU Radio certainly is the top side of that. So fortunately, the GNU Radio Companion is a data flow architecture. And data flow with some additional features is what I want to talk about this morning. We can make radios truly cyber secure. But what does that mean? It's kind of like self-referential consistency. How do you bring that in? Well, you've got to throw away general recursion. You've got to throw away general purpose computing. So wherever you have an Intel chip that has go-tos hardwired in, how many of you know how many different instructions, different families of instructions are in the current Intel chipset? Anybody? There are numbers. Somebody here must know. That's for cyber people, doing cyber hardware. John Erickson wrote a book on cyber, and it's a 300-page book. The first 200 pages are detailed explanations of the hardware. Why? And I quote him, quote, bits are bits. And as soon as you stick these bits on the hardware, it's going to do exactly what the bits say to do, regardless of what it's supposed to do. And so the last 100 pages are hacks. How do you do stack overflows? How do you do the no-op sled? How do you do these hacks that the hackers really understand? And why do they work? Because bits are bits. And the CPU is not self-referentially consistent. It's got general recursion. It can do anything imaginable to compute, and therefore we got to get rid of it. And we can, but first of all, I want to talk through why we got to do that, and then what we can do if we, once we do that, like a new radio community would be able to offer truly hackproof wireless stuff to the world. I think that would be a big deal. And so here's the first part of doing the math is understanding where the breaches come from. So there are three basic threats. One are the network threats, and those are the hackers that get in remotely. The second is the insider threat, Snowden or whoever, and there are tools now like Gravity and others make software that monitors the network and what people are supposed to be doing based on their roles and what algorithms are supposed to do, and will raise a flag if something seems to be going wrong. So when all that data was being exfilled from Target, there was a flag was raised saying, "Hey, that's a lot of data going out of the system," but it was too late by then. And the third one are supply chains. So if malware is in your system from the start, then you're really in trouble. A couple of years ago, NIST began to publish on advanced persistent threats. How many of you know what an APT is? Okay, great. So the rest of you are going to know in a couple of minutes at a next level of detail. It's crucial to understand the APTs. So APTs are designed not to wreak havoc with your computer, but to get inside, to get as close to the operating system, under the operating system. Rootkits basically say, "Hey, I'm part of the operating system." And they have the template to make it look to the operating system like this code is actually part of the operating system. Is it? No. How is that possible? Because general purpose computers are self-referentially inconsistent. One of my partners in crime here on Hackproof is Mike Wynn. So he was the Secretary of the Air Force who got the Air Force into cyberspace. And when Mike told me to, try to do something in the cyber defense realm, I said, "Well, Mike, it's impossible." And he said, "What do you mean it's impossible?" I said, "Well, you tell me whether the following sentence is true or false, and I will solve the cybersecurity problem." Quote, "This sentence is false," unquote. Is it true or false? Well, if it's true, it must be false because it says so. And if it's false, that's a double negative, so it must be true. So it's self-referentially inconsistent, and that's what operating systems are. From the iOS to whatever. Why are they self-referentially inconsistent? Because of the hardware. So you go diving down inside, like Eric says, and you find the go-to. So go-to allows infinite looping. And as soon as you have infinite looping, where you're not managing the resources allocated to a task in a precise way, so that you know what it's supposed to do, and then when you observe it doing something otherwise, you can say, "Aha, this is bad." Then you've got a problem. So because of that, APTs come in as images, they come in as attachments, click on an email and so forth, and they go in. What's their goal? Their goal is to get between the hardware and the operating system. Because as soon as you're part of the operating system, you're golden. And so you can read up on the, NIST has 3 families of publications now. The Federal Information Processing Standards, or FIPS, and 140-2 is my favorite FIPS. It is the standard for crypto modules. That's been around for quite a while. And now the 800 series has been published recently, but a month or 2 ago they came out with the 8000 series. So the 800 series are a bunch of recommendations and advisories, and they say, watch out for APTs, and here's why they're so nefarious. Their job is to not mess up their system, but to get in there and hide and to escalate privileges and to continue to provide this outside access so that the money flows out. In addition, though, the software aspect of this is as you add these layers, you're adding layers of inefficiency. When I first thought software radio, people didn't really have much in the way of high-quality instrumentation. So I did a lot of measurements on hardware. And so when you go from bare metal, somebody who really knows the OS and the actual machine code, you do better than a compiler, and especially the compilers of a few years ago. And therefore, you get a certain level of capability and speed. And then when you go to higher and higher levels of programming, you get to lower and lower speeds with respect to the hardware, so you get these slowdown factors. And my experience has been every time you go another level up, you lose about a factor of 5 to 10, depending on how good the compilers are and so forth, and speed. And so when you actually do the measurements today, it's not actually 6 orders of magnitude, but it's more like 1,000x between bare metal, highly optimized, and software defined. So that's a price that we're happy to pay when we have plenty of MIPS, and historically kind of MIPS have been free. But because of the nature of the operating system and the CPU, so it'll give you 1 CPU or 10 CPUs or 100, every time we get clock stall, we go parallel. So the first clock stall that I ran into was maybe 20 years ago, and MPI, the massively parallel interface, was invented, and people started to go parallel. And then what happened? Well, breakthroughs, and the clock started going up again, and so everybody forgot about parallel for a decade or so. And now we've been in clock stall for several years. 2 to 3 gigs is about it. There may be some incredible nano breakthroughs that will get clocks up into the, tens to hundreds of gigahertz range, but not so far. Now, I'm actually consulting on some superconducting electronics where the clocks start at 40 gigs and go up into the 100 gig range, so you never know. We may get out of clock stall again, but for right now, we're in it. And therefore, you got to worry about how the code, these advanced persistent threats, move around. And this is an example of a timeline where we have the CPU, and so you've got the hardware, the instructions, the interrupt service routines, which are part of the drivers, and then you're pushing and popping the stacks. And so here's some examples of where the APTs like to hide. And the reason is because it's a Turing machine. And the general capabilities of a Turing machine are indicated here. This is from a paper that I did for the Defense Science Board a few years ago. So when Jim Gosler was running a Defense Science Board in 2012 on cyber, he wrote me a note and he said, we're going to proving that cybersecurity is impossible. You want to send me, write me up something or send me a copy of that. So I wrote up this paper where I, for the Defense Science Board, proved that cybersecurity is not just hardware, it's impossible. Why? Because general purpose computers have all these 7 capabilities. Do radios need all 7 of these capabilities? Class, what's the answer to that question? No, they don't. Why? General recursion at the bottom is a general minimization. So that means start at some starting condition and go until you satisfy some result. So my favorite example is 7/7 pi. So we know that pi is a transcendental number, and the decimal expansion of pi goes on forever because it's transcendental, it never stops. How many 7s in a row do you get in pi? Well, last time I looked, there were like 5 7s in the decimal, but not 8. And so the question is, are there 7 7s in a row in the decimal expansion of pi? We haven't found it so far. So you start heading down that path, and what do? You keep burning MIPS until when? Forever. So I've written code like that. I once wrote a program that was supposed to increment this number up to 10, and so a little routine, add 1 to x until x equals 10, and then that was it. Pretty simple program, right? Until you call Stack Overflow. So we all write these girdling police things at the bottom, but we don't need to do that. And I mentioned this sentence is false with Mike Quinn, which is the halting problem. So what you can do, though, is throw away that degree of generality that you don't need. And what that means is that instead of while and until constructs that are open-ended, you write iterations. Like I'm a Ruby programmer, and so I like .each. And what .each does is it checks to see how big the array or whatever it is that you're using is, and then it iterates down. So it's finite iteration. So we replace open-endedness with finite iteration. What about in the operating system? You have to say, until false, so you're intentionally being open about the whole thing. Well, that's so that the software can recognize a hardware interrupt. You got to have the software running, or it's not going to recognize the interrupt. What's the situation on an FPGA? You simply wire the logic to the port, and when the line goes high, that's the interrupt. And so when you think of this in terms of hardware, and the hardware initiating a task for state changes, you no longer need capability number 7. This is really important because the new radio has this sort of capability built in. And therefore, we no longer have the halting problem. Why? Because the hardware, the radio that we're going to build, is no longer Turing equivalent. You can't do anything possible to compute on a Hackproof cognitive radio. So what apps do you throw away? Well, I'll show you. You don't throw away any apps. You actually wind up keeping them all. There's another feature besides this sort of Turing thing that is pretty important. So I was at Stevens Institute of Technology, and I was their research director. I had time to think about some of these things and interact with computer science and LD communities. And one day I realized, I think I have a proof that even if you threw away the while and until, you're still dead meat with a general purpose computer because of the instruction set architecture. So if you have a state machine, which is what the registers are, and actually the memory, just think of the registers as a general purpose CPU. If you're given the bitmap of the contents of all of the registers, is the very next contents well defined? Yes or no? Yes. Why? Because it's an instruction set architecture. The hardware is wired up to take a certain state of the registers and to give you the next state. It's exactly the same thing as the natural numbers 1, 2, 3, 4. Given the number 5,379, you know how to add 1 to it? Plus 1. You get to 80. That's called a recursively enumerable sequence. So I wrote up a little note to my heads of my EE computer science department, and they said, well, more or less they weren't sure what to make of this. So I'm going to know Carl Landwehr at the National Science Foundation. How many of you know of or have interacted with Carl at all? So at the time, Carl was the head of theory of computing for the National Science Foundation. So I wrote Carl a note and I said, hey, Carl, I think cybersecurity is mathematically impossible. And I had this little proof, so I sketched it out. And he said, well, you better, so I don't have time to really dig into it with you, but go talk to this guy at Carnegie Mellon or somebody at Michael Bedford or Jay Ligotti at the University of South Florida. So I'm a Florida guy. I forwarded this to Jay. He said, sure, come on over. So I went to the whiteboard and I drew the chart that you see there on the whiteboard. So here's CPU, here's the instructions that keep going, from one state to the next. You power it up and you kind of leave it on. And I said, I think what's happening here is we've got a recursively enumerable sequence, just like the numbers 1, 2, 3, 4. And Jay smiled and he said, I know what you're going to do. And I said, yeah. And so he said, everybody knows this. Wait a minute. So the way that this works is you say, well, and Jay is the guy who's published the most on monitor systems. So a monitor system is hardware or software, it doesn't matter. It looks at the state of a processor and says, is this state safe or not? And if it's safe, then it allows it to keep going. So there are all different kinds of monitor functions, so we'll do truncation and other things. And Jay's the theory of computing guy on that. So I said, therefore, if a monitor function works, then you must have these predicates that say this state is okay, or this sequence of states is okay, and this other sequence isn't. And he said, yep. So if you listed them all down, these are not okay, and these are okay, then what do you do? Well, because this thing is a recursively enumerable sequence, and you never know when you're going to power it down, it's open-ended, just like the numbers 1, 2, 3, 4. So I'm going to take a diagonal, and this is called Cantor diagonalization. So if the state of this not okay set that you've got there is a 0, I'm going to flip it to become a 1. And if it's a 1, I'm going to flip it to be a 0. I'm going down that diagonal. And I'm going to take this template. Is it okay or is it not okay? Well, I don't know, but I'm going to try to find out. So first I'm going to look at the first item up there. Does it match? No. One bit is missing at least, others may be different. And you keep going down, 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 and no matter which of the this is okay, this is not okay tests you run, you find out that it's not one of them. So what do you do with this new template that you just made up by inverting the diagonal? Add it to the bottom, right? It's one that you hadn't seen before. And then you keep going like that. So this is called an undecidable set. Undecidable. So most people who are in computer, in IT security and so forth, when I use the term undecidable and kind of ask them in the sidebar if the set's decidable or undecidable, they really don't know what I'm talking about. You have to kind of get into theory of computing and really understand that this means that no matter what code you write or hardware you build, it's impossible to quote Gary Cantor, not even God can do it. Because what you have to do is what's called power set of the integers, meaning the set of all the subsets of a recursively enumerable sequence must be written down or you can't do cybersecurity. So that's another reason why it's impossible. So not only do we have to get rid of the while and until these open-ended constructs, we've also got to get rid of the registers. How do we do that? Well, again, to go to McGuire, we can fix this. How? Kind of going back to bare metal. My favorite chip now is the FPGA. I don't care if it's Xilinx or Altera or whoever. But if you connect an FPGA to the internet and then parse to extract the text of the packets, payloads, and then put them together. If you see GET, that's a GET request. That would be HTTP, and also you all know the TCP/IP what a sync request is, right? That's why I'm show of hands. I want to see if I'm losing the audience or not. No. Okay, so still pretty much there. And then if it says get, dish out the HTML. How hard is it to do this? Well, it's not hard. Turns out that Mike Wynn and I formed a little company called Hackproof. And when I started trying to sell this Hackproof system to DoD, finally got to Neil Deering at NSA, the chief technical guy at NSA's Information Insurance Director. And I said, and so this was over a year ago. And so what I want to do is I want to teach the defense industrial base how to build this stuff. And he said, well, we don't compete with industry anymore. What do you mean you don't compete? I was a co-op there. I used to wire computers. We were competing with industry all the time. But we don't do that anymore. So he said, the best thing I can tell you is go build some and we'll buy them. So it turns out that we did build them and they're not buying. You heard that before? So we did, and it's built on what I call the blade after next. So this is Apple's Microsystems is our subcontractor, and they're using Core and this is the architecture. This is a screaming board. It's got 3 Xilinx U7s on it, and it'll do. So we ingest bits. We kind of tone it down from 40 gigabits a second, which is what the board is built for, to a gigabit a second, and it serves up, it ingests everything the internet can throw at it at a gigabit a second. You can go to www.hackprooftechnologies.com and talk to the board. It's sitting in my lab in Cocoa Beach, and it's been hacked by Anonymous, by sites in China, Russia, everywhere. Not only that, the Air Force attacked it. Why? Because they're the Air Force. They called up his buddies in the Air Force and said, "Hey, we got this, thing online, and we think it's secure. Why don't you give it a try? Tell us if we can get in." And so after a couple of days, they called up and they said, "Okay, what's the deal?" We're like, "Well, actually, there was no computer, there was no operating system." I think I have that on these slides, right? There's no CPU, there are no registers, there's no operating system, there's no random access memory, so lots of memory. In fact, we can do 1 million simultaneous transactions because of the incredible power of that board. Why? Because we have a RAM, and it happens to have a content-associated memory. Yeah. So IP address comes in, it says, I'm going to point to this block over here, and so memory is dedicated to that transaction. We can build radios like this, and in fact, this is what my vision of GRC Cyber Solutions is. Okay, so the rest of the talk, that was the first half of the talk on doing the math and why we really got to go this way. So is there anybody who doesn't think that we actually need to dump the general purpose computer and get onto bare metal GRC blocks that are mapped into bare metal? Anybody not agree with that? It's okay. I can't believe I got the whole way. No guts, no glory, come on, no complaining.
The prototyping aspect of the general process. You can't get the speed of development.
True. So where does our website come from on this machine? The answer is general purpose computers, we're there playing around with these software tools. Why is that okay? Well, you get so much capability from general purpose computers that it's not even funny, and you can't get weaned off of that instantaneously. So this board is the blade that serves the web pages after they're designed and built. But, and it looks like this. So you've got this flow, and you've got this interaction with the user, and it's all self-referentially consistent and checked and all that sort of thing. But the personalities actually come from general purpose computing offline. And as I'm sure all of you who are at PGAs know, that these things can be partially reprogrammable, partially reconfigurable. So, a quarter of the chip can be having a bitmap going in while the rest of the chip is doing its thing. But if you're really, if you push Xilinx really hard, they'll show you how to configure it so it's no longer field reprogrammable. So if you have it there and you set certain bits and change certain things physically, now it's really wider. So that FPGA personality is in there, and you actually can't change it. So that's what we have here, FPGA personality in, and then it becomes hardwired. The development environment for rapid prototyping is still neat. But then, what is the target going to be? So I was talking with Matt yesterday and said, could you run a GNU radio rapid prototype GRC chip without the general purpose processor in the loop at all? And he said, yeah, we could. So I take that as a Hackproof GNU radio is possible. But to do it requires some extra shenanigans. So I want to talk for a couple minutes about that. side act learn, and if you don't have the learning in there, then it's not going to be very flexible. And we can build learning into a web appliance, into the hardware, so that it can modify its own behavior. But Charles Clancy was the one who wrote the first paper that I'm aware of back maybe a decade ago on how to deceive a machine learner. So if you get machine learning and then you have these decision surfaces, and if you change things a little bit at a time, you can get the decision surfaces to move them so you can get it to like itself. So you got to have some kind of DNA. So in these patents applied for, we have a description of machine DNA, and this is an example. So at the top it says, here's what an e-commerce machine is supposed to do in text, and then the self-referential, and then the self-description talks about things, places, paths, actions, and causes, and there's a nomenclature for it. I was digging through the start-out GRC files last night. The GRC would be a perfect way of representing this stuff as well. HTML works fine too, so there are many ways of representing the DNA. What we've got to do is you've got to bound the surface, and you've got to define these decision boundaries a priori, and you've got to have them wired into the machine. So this DNA, in our machine is actually hardwired in. It's not modifiable. So the machine can't unlearn its own DNA. It can modify its own behavior, especially in response to interaction with authorized users, saying, okay, you don't recognize this condition, but it's valid, and here's what you need to do. Or unsupervised learning, conceivably even deep learning, although I haven't really dug into that very much. Well, how could we build one? I think RF Knox is perfect, right? So we've got the crossbar switch and the egress interface, and then hang the pieces off like the radio port at FP. And thanks to Jonathan for providing me with the starting point that I hacked up a bit. I'm sorry to hear that the RF NOC is closed for the tutorial. You said that there are only 70 seats, but I'm really glad to see the capability that's there, because with this level of capability, instead of having to have general purpose computing with all the advanced persistent threat and all the attack surfaces on your delivered radio that comes from the GNU radio community, you can cut the umbilical and have a hackproof GNU radio in the FPGA, and seems like that could be important. So in addition to just... Sorry? I don't know. Jonathan, where are you? What size is the bird? I was hoping nobody would ask. Or, Tom, do you know what I do? I have no clue.
Removes the uncertainty.
Hey, here's Joe. Do you know what Heisenberg is? No, I don't either. So. Great question. Jonathan will be glad to answer it in the break. Okay, so Cyber Solutions. So you've got to have machine learning, and for machine learning, that model. Okay, so I proposed this to Chip in 1997, right? So I'm used to being sort of a candle in the wind, but I mean, it's been 15 years, and can't we get this thing built? Where the radio would get this upload, an app, an IP block, whatever it is, and examine it and determine, hey, this looks okay. If it looks okay, that means it meets these criteria that are built into the self. What is the self? How do you generate that on FPGA? So I had the pleasure of having a couple of drinks with an active dinner with a couple of guys from AHA last night, and they described regex for regular expressions. So you parse regular expressions in real time, evaluate them against what's going on, and determine at every step along the way, is this still a valid chunk of data for whatever the flow is supposed to be. Also, there are some companies like Coherent Logic that have tried to follow the Harvard architecture where you separate data from control. And while that's a step in the right direction, it really doesn't solve the problem in the same way that the bare metal mapping of modules to IP cores on an FPGA would, because the contractor, and so my first job was to create the airborne reconnaissance strategy, and we worked for 60 days, and we created it, and it was like a 200-page document. And a couple of days later, I'm walking through the Pentagon bookstore, and I look over, there's my report. It's like, the airborne reconnaissance strategy is for sale in the bookstore for $40. So, I didn't buy it, but I went back to, I even had the appendices that weren't published. And so I said to Vic D. Marines, who was just the head of the center then, you had become head of MITRE and all that, I said, Vic, they're selling our report. He said, Joe, did you assert DOD's copyright? Deer in the headlights, right? What do you mean? He said, well, look, if you don't assert DOD's copyright, then anybody can copy it and sell it. Makes money. And, you know, that's the way capitalism is. And if you invent something and you don't patent it or otherwise address that, like getting it into the public domain in enough detail so it couldn't be patented, then one of the big defense contractors will. They'll throw a little bit of R&D at it and they'll patent it, and guess what? For the next 17 years, it'll be sole source to them. So I said, wow, okay, Vic. So from now on, if it's worth reading, I will copyright it on behalf of DOD or whoever my sponsor is, and if it's worth building, I will patent it. So patents applied for. Why? So the good radio community can have the benefits of this architecture and implementation approach without having to pay tons of money to some big guy. And actually, Mike Wynn and I formed this company. We did this Hackproof web machine. It is a for-profit entity because it's almost impossible to create a not-for-profit entity in this space. But we're started in the public interest, and the public interest today is sharing the knowledge. So digging a little bit deeper into RF NOC, the GRC can handle complexity very well. And I was really impressed yesterday. I hadn't seen the kind of tutorials and the progress that we've made on GRC. That's kind of the default development environment. And that's really terrific because now instead of mapping just a Python or whatever, you can map to IP cores back on the FPGA, get the bare metal quicker. I'm working with a Tyler company and another couple of entities for doing that kind of thing. The level of complexity, LTE and so forth, is really awesome. As I mentioned a minute ago, data flow alone is really not enough. You've got to have the block diagram language, and we're getting there with GRC and other tools. And Atlas Microsystems uses their own environment called Torfire. So that block diagram that I showed of the web machine, and that is a hackproof web machine. It's been online for a year, and as I said, it's impossible to hack. Now, would it be vulnerable to an insider threat? Sure. If I want to put stuff on the web page that I shouldn't, I can. And is it vulnerable to a supply chain attack? Well, when we're cooking up, is our Xilinx tools vulnerable to supply chain attack? They have to say yes in principle. But then when you build parallel pipelines and allocate memory and so forth, how challenging would it be to put stuff in that kind of an architecture that has self-checking built in? So the key is self-checking every step of the way, and that's a challenge. Also, skill mixes. So interacting for the past year with IT people, I've come to discover that I was really lucky to be a double E. Who took theory of computing? That doesn't happen very often, I guess. So I'm looking at this, at these traces, and I feel very much at home. But others who are not quite as used to this are like, well, how do I do hello world with that? How do I do hello world with that? There's a skill mix in there. So the ability to visualize what these flows mean then becomes really important. And, thanks to Mitola for helping you with some block diagrams that help bring that out. I believe that innovation is within reach, and I've only been kind of preaching this for a couple of years, so typically it's 5 years from candle in the wind to everybody says, yeah, that's what of course that's the way to do it. So I think I got a couple of years to go, but I believe that innovation is really within reach. The data flow tools are really getting there. I MATLAB Simulink and other tools like Forfire. We need better tools though, and we need to better educate the communities, especially the cyber communities. How many of you here are interested, directly or indirectly, in cyber one way or another? Ah, come on, everybody. Because everybody is these days. Why? Because we're enmeshed in all this stuff, and things are getting ripped off, and these APTs are all over the place. And so we have to care. The networks, though, create challenges beyond the node. So even if my node is okay, having the DNA for the network and having the protocol stacks so that they're not open-ended and you don't have heartbleeds bleeding all over the place, that's another challenge. And actually, GNU Radio and the GRC help with that. Because when you build a block diagram, it's got outputs. And so with just a little bit of extra, as Tom was saying, you know, when a compiler does a dump, it dump. So the GUIs that enable us to more quickly get to the relevant part of that dump would help us build code in block diagram languages where there are no heartbleeds because it's just not possible. You're asked explicitly what is the number of bytes that are allowed. And if you say the number of bytes that came in plus 1, that's a good thing. If you say 64 kilobytes, then that's a human programming error, and shame on us, but at least we have really raised the bar on how much technology, how technology helps. So I think data flow plus you gotta have trusted tools or your supply chain is in trouble. I'm calling hardwired, which is modifiable from cycle to cycle, which has machine learning built in, software. It's not software, but it is not inflexible either. Bare metal that you can modify in real time, what's that? That's kind of a new construct. And if you put machine learning, machine DNA in there, you can do this. So, tools. The paper that I did for the Defense Science Board was a category theory of cybersecurity. How many of you are really into category theory? I didn't think so. Hey, well, it seems I had a lot of time to just kind of do research, and so I spent some time in category theory and came to discover, you know what? I was using this stuff back in the early days. So when reverse polish notation was kind of big and the signal processing toolkit hadn't emerged into MATLAB, I did a research project. So we did basically a Hewlett-Packard calculator for signal processing. We did it on a 32-bit computer, which in the 70s was a really big deal. And what we did was we said, basically, we're going to define all the domains, all the signal processing domains, vectors and arrays. And then for every function, like add, we're going to have an inverse, like subtract. And we're always going to keep the last thing that we did, so you could always back up one. And so armed with that, we did a cheap programmer team operation, which in the 70s was a big deal. So 4 of us wrote 100,000 lines of code in 6 months. We used it for a year and never found a bug. Never found a bug. It's the most successful software project I've ever been involved in. And why? It was because we actually thought about it and we applied some mathematical principles of define the domains, define all the maps, and then simply build it so that it has the mathematical structure you've defined in advance. And wow, you can really go hard. So Ada tried this. You programmed in Ada. Okay, right. It's still in use, by the way. Safety critical stuff in Europe. At one time, a couple of years ago when I checked on this, Ada was actually a requirement. So Ada lived in Europe a few years ago. That's a strongly typed language. I program in Ruby because I hate typing. I hate to have to think about it in advance. So coming up with the software tools where you can play around in Python or Ruby or whatever when you're in discovery mode and don't know exactly what this thing should look like. And then rapidly transition to GRC block diagram mode and map it to the bare metal and then have software bare metal. To me, that's the future. And if we can get that done, you know what's going to happen? So I'm a software radio guy, right? And I built my career on saying, hardware is the big deal. Back in the 70s it was. The software was right on top. And pretty soon, over the next decade, software will be this big, and the hardware will not be as much of a big deal. And that's the way it is today. Hardware is commodity stuff. But I believe that from here going forward, that we're going to have we're positioned for a big shift, what I call app-enabling shifts. So this, if you visit my Hackproof website, what computer are you running on? You're interacting with a special purpose machine. It's an HTTP/HTML machine. All it knows how to do. It doesn't know how to do anything else. But if you send it a SYN request, if your browser interacts with it the right way, and then a GET request, it'll deliver you the HTML. What's between the bare metal and this app? You don't need all that operating system stuff if you don't have a CPU that has to share, and you don't need drivers. You don't need any of that stuff. So this is my vision of the future. And if we could do it in the GNU radio community, then what could we do? Well, a lot of pretty exciting stuff. First of all, SCADA, Internet of Things, there are all kinds of vulnerabilities. Everybody loves wireless, but it's so hackable it's not even funny. Hacks having to do with length of passwords and that sort of thing have to be dealt with in the crypto domain. But hacks having to do with the fundamental vulnerability of networks to advanced persistent threats, general purpose computing that has this malware built in, we can really slam the door on remote exploitation by adopting this enhanced Hackproof GRC. And so all these kinds of applications that are shown here, which I'm sure you guys can invent more, would then kind of come into the fold. In addition, there are a couple of other exciting things. Quantum computing. I was visiting a quantum computing group, and I said, why do you guys want to talk to me? They said, well, you're the software radio guy, right? I'm like, yeah, but what does that have to do with quantum computing? This is, millikelvins. And they said, well, we now have the coherence length of these qubits up to, on the order, I think, of microseconds, right? So what we do is we create this waveform, and we pre-distort the waveform so that it'll go in, and it'll basically put the data in. This is RF, this is microwave stuff, 7 gigs, I think. It'll stimulate the qubits, and then compute, and then read out the qubits, and it's a radar pulse. So I'm like, wow. I was delighted to see a board up there. If I got her name right, Linda Mullen, are you here by any chance? Maybe not. So, Naval Air Warfare Center doing lasers underwater. That's a good, nifty arrangement. And they are doing basically LiDAR, underwater radar with communication. So RF convergence is important, and being able to do multiple functions with the same platform is rapidly emerging. So I think quantum computing, space-based computing, and those kinds of applications will all be domains for new radio in the not too distant future. So my parting shot, this is my last slide, and I've got 5 minutes to spare, which is unusual for me. Let's take it up a notch. We are just uniquely positioned to make a really big impact on the community. GRC is about that far from Hackproof. Try to acquaint you all with the theory of computing enough to realize that there really is a line with dirt. If you have a general purpose computer in a delivered product, then there's an APT in it. I mean, there is an APT in it, or more. You haven't found it yet because it's a 0-day attack, and you won't discover it until the command and control or the conditions are met for that malware to do its thing. But if there is no such computer, and you have the GRC block diagrams mapped into the bare metal with some machine learning and some flexibility and some user interface and all that built in, just visit the website. It's got a user interface, allow your browser, and over time we're going to keep developing that to show what can be conceptual model for what any radio could do is the Wild Wild West was the Wild Wild West until when? Anybody? History buffs here? What really changed the Wild Wild West into the not so Wild West?
Railroad.
It was the golden spike. It was the railroads, yeah. Because railroads made it so that instead of having to defend yourself in a wagon train forever, all you had to do was really defend the rails and go achieve just the talking wires that were obscuring the sky. So we had, we were putting Morse code and telegraphy all over the West. So it was the communications and the fact that instead of having to defend everything everywhere from anybody, all we had to do was really defend the rails that we moved. So I look at GRC especially and the RF NOC as the rails on which we can really build a safe internet. And so I hope you guys are as inspired as I am to try to go get it. Thank you very much for your
I just wanted to know, based on your experience in quantum computing, like how far are we from actually having, I know D-Wave put out the quantum computer, and Google has a lot of research going on quantum computing. How far do you think we are away before we can actually have, a quantum computer that researchers are going to be able to actually, do HPC type stuff on and that?
Thanks, Juan, and thanks for the input on Reggae last night, by the way. Okay, so quantum computing, to me, originally meant Shor's algorithm for breaking RSA and that kind of thing. When I was visiting this quantum computing group, and they have lots of qubits and so forth, and they said, well, Shor's algorithm is the last thing we want to do. They had a whole bunch of other different algorithms, and because of clock stall, two things are happening. One, massively parallel is back, which everybody's got cores and lots of cores in parallel. But we're also going to physics. So I believe that before we have qubits that will actually have superconducting supercomputers, if clock stall survives another few years, if the NO breaks through and you can get 100 gigahertz clock on a supercomputer chip, then forget it. We're done for another decade or two. But if we can't figure that out, then I believe that superconducting supercomputers will be here sooner rather than later, and it won't be too long before big companies and universities and so forth can have their own superconducting supercomputer. To get to qubits, you've got to go from room temperature down, and the way that this kind of works is down to around 60K, and then down to around 4K, and then down into the millikelvin range. So you're down into like 10 millikelvins, 20 millikelvins. And it's literally like that. So in the one room that I was in, room temperature's up there, and when you get down to here, bottom of this large vesicle is 20 millikelvin. But it's all cold, and so you can put chips all the way up and down this stack, and while so even if the bottom, the true qubits, don't materialize soon, I believe that other supercomputing has the potential. It's the economics. So the laws of physics are good, but the economics is the big question. So if anybody knows whether we're going to have nano at 100 gigahertz, that's the answer. The answer is yes, and the answer is no, and vice versa. Okay, thanks for that question.
Anything else?
Thanks. So with the state machines, without the state machines, you have your metal, you still want states. Doesn't the security open up out on the cookies that you have on the receive side? Isn't that where the whole moves to?
Yeah, so that's a really good question. You don't get rid of state. So a Turing machine is a state machine with semi-infinite tapes because it's generally recursion and it may go on forever and it's partial. So it may not return a solution. But the state machine that's part of that So a primitive recursive algorithm, or the kind of iteration I was talking about a minute ago, a Ruby.each statement, uses state. So I did not mean that these machines don't have state, but the state machines are built in lookup tables. So when the GET request comes in, the IP address goes into this content, this CAM, and it points to a block for that session. That's state. And then the block of 2K bytes up there is dedicated to that purpose. So it's not randomly accessible memory. There's no other way to get to that particular chunk of memory other than by this pointer. And that chunk of memory, because of the way the pipes are built, can only be used for that transaction. So as transactions are building up, the CAM has IP addresses in it that haven't timed out, and therefore they point to different blocks of memory. So yes, you have state machines, and the state machines are doing that kind of recursion, but because the recursions are tightly bounded, they only last for n times, where n is the length of the database or whatever. It could be 1 million, but if it's 1 million, then you know exactly what resources go into each one, or you can bound it as a function of the tree, and therefore the resources are available to get the job done, but there aren't any general purpose unspoken for resources in that machine. So yes, you do all the state, and that's the way it works. Hopefully that's a better clarification of how it works. But once you do that, then the Cantor diagonalization goes away, because nothing is semi-infinite. Your state machine will keep changing state, but it's not in the same, it's not recursively enumerable, because it is one constraint or another, and therefore you're done. So for example, if no data is coming to that machine, it stops. Literally nothing is going on. So it's a data-driven machine. Therefore, the recursive enumerability and the Cantor diagonalization and all the rest of that lets the hackers in, because the resources aren't being used and they aren't accounted for. And then you're good to go. Okay, so thank you very much.
Yeah, one more question over here.
Oh, okay, sorry.
So aren't there some things that you just can't do without possibly infinite iterations? I mean, aren't you binding your hands a little bit? One example I can think of is like a DSA system where you're pulling different channels until one's available. Could that last forever, or could you just be sitting while all the channels are idle and that could last, 5 seconds, 2 hours, who knows?
Okay, so if you're polling, then there's each of those channels has state. And if you do a data-driven machine, then when the state becomes available on one of those channels, the channel is connected to this machine, and so it recognizes by the interrupt on that channel that that channel is available. If the channel has no such capability, then by building a machine that would iteratively poll, while that lasts forever, it's not the open-ended recursion of that leads to the Cantor diagonalization, because you have a certain number of channels, and this state machine is obligated to iterate over those channels and to provide some results back to the rest of the system, correct? So that state machine itself is bounded and is aggressively finite state, let's call it, because it just can't do anything else. So if you have those state machines all over the place, like the Speakeasy 2 source code that I wound up on our reverse engineering help Mitola and their Speakeasy 2 program was full of state machines. It's fine to have those state machines. You're sitting there, waiting for squelch to break so that you have a signal present. That state machine just sits there. It has a very specific job to do. It's integrating this stuff, and when the noise becomes then that's all it does. And therefore, there are no general purpose. You don't need general purpose to do the real job. And I guess that's my real message here is that because of GNU radio and wireless communications being so well defined, there are things that are open-ended like squelch, right? You have to sit there and wait for what happens. But the state machine is tightly bounded, and that machine will talk to something else according to some easily specified rules. And every place along the way, you can have some regular expressions or other lists or whatever that describe what is allowed. And anything that's not allowed is disallowed. So this is whitelisting. Think of it as whitelisting communications. Today, general purpose computing is blacklisting. You say, oh, not allowed. Well, with this architecture, everything's whitelisted. If it's allowed, it's in there. If it's not in there, then by default it goes to the trash bin. And the states and the control of the system are designed to make that happen. We have our log files and we go look to see what the hacks are on our machine. And it uses up 100 megabytes a week. And it's fun to kind of read through and see where the things are coming from. But it doesn't affect the machine. So that's the answer on stage. Once again, really great question.
What's
Looks like we got another.
And then we'll probably break for.
Yeah, 5 minutes into the break now.
What about more hardware-based attacks like on FPGAs? Like I think it's called differential power analysis. That's where we break down the wire versus something like how it's connected.
Right. So differential power analysis is a way of examining what a piece of hardware is doing, and from that determining what's going on inside. So the type of threats that Hackproof GNU radio would protect you from are the usual cyber threats, data and messages and that kind of thing. If FIPS 140-2 says that you have to, for a cryptographic module, you've got to have defense in depth, you've got to have tamper recognition, you've got to have this long list, including the original version of 140-2 came out and said you got to do a threat analysis and layer your defense according to what you think the threat is. So if you think that power analysis is a threat, then you need to build that into the architecture. This approach to GNU radio would protect you from network threats and from malware in the supply chain, in the general purpose computing supply chain, but not from malware in the FPGA supply chain, nor the certain other kinds of threats. So that's a legitimate question. Now, if you were using the profile to say whether malware could be present or not, then that would be a good tool, because the FPGA is going to have a power profile, and based on, depending on what the state is, you should be able to do power profile matching. And if all of a sudden it started misbehaving, then power profile could be a really good way of saying, this chip doesn't look right, and raising a flag for further investigation. Very good question.
All right, let's thank Dr. Mitola again.